the first left side singular vectors, the only columns that matter are the first n, and we can call those Rn. Okay? The first n columns are the ones that matter. And then we can also convince ourselves that it's only the first n rows of this, let's say the first n columns, and here the first n rows of S that matter, and this is Sn transposed here. So we find therefore that H0 is also equal with these multiplications to Rn sigma n Sn transpose. Okay? At this point we haven't eliminated anything. This multiplication will give exactly the matrix, just like the original multiplication would. Okay? Now, in order to ensure that alpha and beta do not limit the rank of H0, we have to make sure that these matrices are big enough. So we have to make sure, of course, that alpha times m is greater or equal to n. So this has to be at least n, right? And at the same time, that beta times r has to also be greater or equal to n. That puts a limit that alpha should be greater or equal to the order over the number of outputs, and that beta should be greater or equal times the order over the number of inputs. Now, you're going to say, or you could say, but I don't know the order. Well, that's true, you don't know the order, because we are presuming we don't know. Yet, these decisions of alpha and beta are really trivial, because what is the order that you might expect to have? I don't know. You think it's 20 degrees of freedom, 10, 15, something like that, okay? Even before we go to the complications of noise, and therefore the order may be 20, right? And you have two outputs, so alpha is greater than 10. Well, but you can take alpha 100. So it's not that you are fighting to just go with the smallest alpha you can. You can take an alpha that is 10 times larger than anything that you could think that you might ever need. And the same thing happens with beta, right? Because the size of this matrix and this singular value decomposition is not particularly constrained numerically by the fact that the matrix has to be so small. And so you can assemble this matrix quite large. So alpha has to be greater than n over m, and beta has to be greater than n over r. And then we have at this point that the singular value decomposition of the Hankel matrix at 0 looks like this. We've made some progress in that we know now what is the order of the linear system that we are trying to identify. It is equal to the rank of the matrix H0. Okay? Now at this stage, we do the following. We say, well, let's write the singular values sigma n, which is a square matrix, as the product of two matrices, E1 and E2. These are two diagonal matrices. Why I keep writing this? These are two diagonal matrices, which then allow me to write that H0 is Rn times E1 multiplied times E2 times Sn transpose. So I am now visualizing here after the singular value decomposition, and I have not stated how I will make this product, right? There's obviously infinite ways that I could take the singular values and make it into a product. I could take all of them to be this and the other ones to be 1. I can do whatever I want. But there is E1 and E2. Now, leaving that decision for the future today, later, we can do this, right? Rn E1 and E2. Now, if we look at the fact that the Hankel matrix 0 is P alpha times Q beta, we conclude that we can select these matrices, which we know what they are, to be the observability block and the controllability block. Now, the observability block P alpha is equal to C, CA, CA squared, etc., right? Therefore, I can see that if I take the first m rows of this matrix, I can call that C. Or CD. Sometimes I forget the D because it doesn't matter. And this is of course AD also, and so on, right? So we have found ourselves a way to get C. So from this matrix, we get CD. Now, we also know that the controllability block is equal to BD, AD, BD, etc. Therefore, we can take the first R columns of this block and call them the B matrix. Right? And so we now have, we get CD from here, we get BD from here. Now we have two of our three matrices because the D we already knew from the beginning, right? It was equal to the observer Markov 0. So we're only missing A. And if once we get A, we'll have a realization of our system in discrete time, right? So there are various ways for us to get the A. Let's take a look at three of them. Extracting a discrete. Okay. Now, the observability block is CD, CD, AD, CD, AD squared, etc. Now, let's say that we call this thing Z1, Z2, Z3, and so on, right? Then from here you can see that Z2 is equal to Z1 times A, right? And you can see that Z3 is equal to Z2 times A, and Z4 is equal to Z3 times A. And of course, we know these blocks, right? Because we've It's not that we know the C and the A, but we know we have a realization for the controllability, for the observability block, right? From here, you can see that you can stack Z1, Z2, Z3, etc. And that times AD is equal to the stack Z2, Z3, Z4, etc. Okay? If we call this matrix L0 and we call this matrix L1, then we can see that AD is equal to the pseudo inverse of L0 times L1. Now, this is one case in which the pseudo inverse does not introduce any approximation because these relationships are exactly true. Therefore, once this matrix has a full rank, there is a matrix that is unique here that maps these things, right? Now, how many do we need going down? Well, we need to make those matrices full rank. So we know that this direction is the system order, and this direction is, if our last one here was ZQ, then that means that we have what? Q times what? Times M, right? So the number of rows here will be Q times M. So as long as we choose Q times M greater or equal to N, then this matrix would be square or tall, and we can solve for the A like this. Okay? This one, of course, here will be ZQ plus 1. So this is one way to do it. That's one way to extract the A. Another way to extract the A is, of course, as you may imagine already, using the controllability block, right? And using a similar argument. That is, we know that the controllability block is equal to BD, AD, BD, AD squared, BD, etc. So, if we call these things, what did I call them? P1, P2, P3, etc., we can see that P2 is equal to AD times P1. That P3 is equal to AD times P2. That P4 is equal to AD times P3, and so on. And then we get PQ is equal to AD times PQ minus 1, right? So if we can write this as being P1, P2, P3. This not to be confused, of course, with observability. This is just a new P, right? Just a symbol. Okay, so we have P1, P2, P3, well, actually, let me call this one Q, and this one Q plus 1 to be consistent. So we'd have PQ over here. And so we have this P's, and what we have is what? AD times P1, P2, P3, P4, PQ is equal to P1, what is it? P2, blah, 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 PQ minus 1, right? Let's see if I haven't made an error. Something here doesn't seem correct to me at this moment. Give me a second.